some of the homeworks are lengthier, some are not, depending on what they are. I feel some of them, I think that last one was only like what, 6, 8 questions, something like that. Not horribly bad, but it's to get the points across. Make sure you guys are getting your learning. So that we're gonna go and look at. Now like I say, we jump back. We're gonna go back and pick up from the beginning here with chapter 5, where we left off from chapter 4. Chapter 5 covers a couple of things, conductor identifications and that kind of thing. Some more of the advanced basics, if you will. And we look at some of the stuff here. Everybody able to see the screen okay? I hope.
Yeah.
Yeah. All right. Yeah, so and again, you're always going back to NEC definitions, right? So we look at conductor identification, and very specifically, they say, okay, what's a grounded conductor? It's like, what does that even mean? Well, when you have a grounded conductor, that's typically referred to as a neutral, right? It won't be grounded like in the runs in the house and whatnot. You basically, when you go back to the panel, that's when you're looking at that. So, and how it's typically identified, usually you'll have, like in a 120/240 case, the neutral will usually be in a white wire. You go up to the 277/480, the three-phase case, typically the neutral is a gray. Excuse me. Or they'll do it where there are three continuous like white stripes wrapped around it, and it could be like a black or a different color, that kind of thing. Never green we like to keep just for ground, but commonly that's referred to as the neutral. And what it does is it sets us up, because current has to have a path to go to. If we didn't have a neutral there, basically you would have nothing happening because current wouldn't have anywhere to go. So what this does is it basically brings us back. Really, I mean, ideally what it does is it brings us back to the transformer outside, right? But the neutral is going back into your panel and then to the transformer outside. But yeah, the neutral in residential is always a grounded conductor. So if you looked in your panel and you go back, and what they'll have, so we have the branch feeds going through a panel, right? And that's where all the line voltages are, your hot wires. Um, Now neutral will be typically set aside. It doesn't go to the breakers, okay? It has no break. You're not allowed to put any kind of switches in a neutral line. Neutrals literally have a straight run back to the panel. Nothing is allowed to interrupt the neutral line. You're only allowed to do switches and stuff like that. Any kind of device controls and devices are only allowed to be run through the line load, right? The hot line. Excuse me. So when you go back to the panel, what you'll have is typically a neutral bar. So it'll be like a long bus bar with a bunch of set screws in it, and so you'll have posts in it. So your neutral wire, and it can handle various sizes of wiring. So you'll see different ones going back to it, but you'll be able to tell all of the lines there are white. And if you are in a case, I don't know if you're dealing with Romex and for some odd reason you don't have the white available. What you do, you have to label it accordingly. And this is where you got your colored electrician's tape. Usually I ran around with, I had, you always have black. Black is a good one, right? Because that's just for taping everything up, your wire connectors and that kind of thing. I always did a tape wrap around every device. So receptacles always got a 1.5 loop tape wrap around the terminals. Switches, same deal, 1.5 loop turn. You want to basically keep the bonding screws on those devices covered. So that way, if you had to pull it out or something like that, it's like a safety precaution, if you will. But good rule of thumb, good practice is always wrap. So you always have black tape, but you have the colored tapes as well. I used to carry around. I had a red, blue, green, and white. Okay, and then black. If I had like a tape roll, um, and the reason being is for identification. So if you had to use like a black line for a neutral, what you have to do is at any point of connection where that thing is shown, you will loop wrap. And they have colored markers out there now too, by the way. I've never really used them, but they have the kind that don't they can, it's almost like a paint, so you can mark a wire with it and it doesn't fade away. So I guess it's kind of like an enamel type thing where it doesn't fade out over time. But I've always used tape, so you would wrap the ends of the wire with white tape, identifying it as your neutral. um, just a little point there, but yeah, that's always connected back to the neutral point of your system. And like I say, there's no interrupts allowed on it, or anything like that. No way to break it with like switches or anything. And that's just a rule of thumb they have. So here's kind of a condensed down picture, right? So if we look from the left, what that represents, okay, when you see those little squiggly lines like that, that's identifying the coil. So of course the outermost one is from the transformer, and then you have the wire taps inside, right? So what they'll do is like the Ameren lineman or whatever come out and tap it, and they'll pull those lines from the transformer, and that's what that identifies. So then you have the three coming in, right? We got our black, red, and white, and it goes to your service disconnect. So we have black, red, and white going into the panel. Notice, right, at no time is there a break in the neutral line. Even in the panel, the breaker, it does not go to the breaker. The breaker has the line loads going to that, okay? See how the black and the red are identified on that? And that's where your break or your disconnect is, if you will. So in neutral, it's bonded there. See that? So in the panel, it's bonded. So it goes back to like an actual ground. So if something were to overload or whatnot, it has a shunt for safety. And then it goes out to your different components throughout the home or whatnot. And these just show different loads. They're not really meant to represent an actual thing. It's just representing that this could be a typical load in a house or something. So the smaller ones would be like 120s, these little guys here. So you would just have one line feeding into it, neutral going to it, and then a ground over protection. And then of course, when you have the 240, no, notice there's no neutral that goes to a 240. You have both hot lines, both branch sides wiring going into that. Excuse me. And there and there. And that's just a typical representation on how to identify it. Keep your ground separate, always green. And color codings, it's important. So that way if the guy that comes behind you 10 years down the road will be able to identify very clearly what was done. And this is the opposite side here. So in the Romex, typically you have it's a very standard 3-wire deal, right? You have a black, a white, and a ground. Um, but in case where you have to use the white wire as like a line load of some sort, right? If you're doing lights with switches and that kind of thing, you have to identify it. So now when you wrap the clear black tape around it, you're re-identifying that wire as a hot now. It's not neutral any longer. And this is to help out for future, like for yourself, if you think you can remember what you did in a house, 5 years down the road. Well, good luck with that. I couldn't do it, but uh, yeah, and you can use they also use something called shrink tubing. So you could do and it's like a little sleeve. It's kind of a rubbery type material. And what you do is it'll fit over the wire here. And then you would have to have like a hot air gun or even like a soldering iron tip, or heck, even to be honest with you, even a butane lighter. If if you hold it over and don't hold it too long, but it'll cause it to shrink up, and it makes a really tight bond. So yeah, you can use shrink tape. I mean, very typically, all I've ever used really is the black electrical tape. It's, you know, it's good stuff. It lasts for quite a while. Actually, that stuff is tough, and it's not very expensive. I have had, you can go out and buy it. They got like an assortment thing where you can get and even different colors of shrink tubing if you decide you like that. But you have to like, it comes in a long tube, so you'd have to cut it to size, and then like I say, usually get some kind of heat onto it. They make these heat guns. They look like blow dryers, but they actually kick out a lot more heat, so you'd be able to quickly seal it up really fast if you decide to go that route. Another thing they talk about in chapter 5, you connecting wiring devices. So, and this is an interesting thing. I used to, when I was doing industrial work, one of our PMs, right, preventative maintenance job orders we used to have to do, um, was go around. We had checkpoints that you'd have to go around with an infrared camera and look at electrical connections with, you know, as far as heat. And if something's getting overloaded, like if even the wiring was running really hot, you know, you'd be able to see it on this infrared camera real easily. Actually, it highlights any like hot points by comparing it to the temperatures around it. But an interesting thing, if you get an electrical connection that's not like really tight, you know, secured down really well at like a screw post, let's say there's a little bit of an air gap between that screw and the wiring where it's got like a little bit of a wiggle to it, right? That will spark off an amazing amount of heat. And over time, it'll eventually, it'll either chew out that wire or it'll chew out that screw because it's causing like little arc flashes, basically, you know, flash points in between where it's not bonded all the way. And yeah, it creates an amazing amount of heat. So if you go by with like an infrared camera, you can see like that you don't have a secure connection, either that or like the device is about to blow. But you always want to make sure that those, you know, like I say, I always give everything a really good tug test after I secured it down. You know, you screw down the wire and it's like, yeah, that looks good. And it's like, not all the time. You know, sometimes you can even, because, you know, if you get one of those screws for some odd reason, it got cross-threaded and it feels like it went down tight, but you still got a little bit of an air gap going in between from the screw head to the wrap of the wire, you know, the little copper loop. Yeah, you'll start getting arc flashes on that little bad boy, and it'll crank out an amazing amount of heat. It's just crazy. And I prefer doing the screw connects. I mean, you got the types where you can just have a straight strip and then snap in the back. You know, you can use that with number 14. Actually, it's the only diameter it'll accept is the number 14 sizes, just because of it's not really reliable. I've never liked using the back little press-in post. I always feel the screw is a really good solid connection. And then making a loop is fairly easy. That's one of the things on your wire strippers. You have so your wire strippers have like a couple different deals on them, right? Main event is to strip different wiring sizes, and you can get them for different ranges too. They make like the electronic style, where I literally had a set that went down to like number 30 up to like 22, I think it was, you know, the really small stuff. And then you get the residential set, right, where it's like number 10 and down to 18, I think it is. Might be 22 on some of them. But you also have, there's like two little holes drilled into those, okay? I know I'm a good wire stripper. And what you do is, so you'll strip off the end of that thing, right? And then you use that little hole right on the very tip of your stripped end and you curl it. So it actually makes a little loop, like a little 90-degree wrap, you know, a half circle. and and then you basically make that loop, and that's what you put around the screw end. and then you use there's like little plier ends on the very tip of the wire strippers. And so once you get your loop onto that screw, then you use those pliers to just sleeve it a little bit down so it makes it a little tighter wrap on the ends around the screw. And always make sure it's oriented whichever way you're screwing down, you want that open end to go with it. Because otherwise what will happen is when you screw it down, it'll end up flaring it out. But if you screw with it, it'll actually pull it in and it makes a really tight connection. And yeah, give it a, always give stuff a good tug test. And that's with, if you're doing a junction box splice, you know, where you got wire connectors and stuff, yeah, give that stuff a good tug test. Don't be afraid of it. If you can't pass a tug test, then it's a shit job. You know, you know, pardon my French, but yeah, you don't want to, if it can't pass a tug test, you don't want to leave it. You got to make sure that that stuff is secured properly. And like I say, it's mostly because of the arc flash. You'll get arc flash can happen in screw terminals and even in connections, you know, where you got to splice and stuff like that. It's kind of crazy. Anyway, oh, we do talk about push-in terminations. They are there. They are, they've been tested, and as long as they're done properly, they do hold fairly well. But now notice, there are restrictions. Really, this stuff is only number 14 and copper, and I mean copper, copper. They have one out there where it's aluminum interior wire, right? And it's copper clad, so like the outside of it looks like copper, right? But the interior of it is aluminum. Junk stuff. It's horrible crap. I hate it. But but aluminum too. I don't really care for that really. And then and stranded. Um, actually stranded. How warn you? Yeah, stranded should not be used in push-in terminals. And to be honest with you, stranded can be extremely difficult to do on the screw down types as well, because a lot of times those strands, once you start cranking down with the screw, it mashes them out and they can become frayed and make short points and stuff. I do not like using stranded running through the house, you know, doing all your branch. I like using solid core because it's just easier to work with that. Now, there are times when you do use stranded, you know, if you're doing like industrial stuff, yeah, doing, excuse me, motor runs, you know, you're wiring up to motors and that kind of thing. Yeah, that's fine. You stranded all day long because it's a lot easier to pull. But for a house, yeah, I like solid core, but yeah, you can't use number 12 on these things either, those push-in terminals. You could try to force it in, and trust me, some people do, and it's just not a real secure thing. And how you, but I do not like using the push-in terminals in the back. I generally just use all the screw-in ones. Just one, I'm old school. They didn't have push-ins back when I first started out. But yeah, I always take these with a grain of salt. They're kind of junk. I call it the home hobbyist cheater thing because they don't know how to screw down on a screw terminal, and then they use the push-in ones. That's fine, but horrible stuff. And then they also see this chapter is kind of weird. It's got he kind of put a bunch of different intro things into there, but these are things you'll run into out there, and it's kind of cool. So different receptacles are different wirings, right? You get some hybrid ones. So the very top one is your very typical standard NEMA, right? National Equipment Manufacturers Association, who they decide like the voltage ranges, and they also decide like so your spades, you know, you have on plug-in styles. So those spade tips, they also came out with a style, and this didn't always used to be, right? Spades used to be of equal size, but on all the newer stuff, pretty much from like 75 on, the uh, the spades are different. One end is larger and the other is smaller, so you can't crisscross on like the hot neutral with these things, which is a good thing, right? So the top ones are very typical, right? So you got the two large spades and the ground connector in there. And again, the new code style is always ground pin up. And then you get the hybrid one, which is the second one down here. Now this one could be with the, yeah, it's a 15 or 20 depending on which way the spade is oriented. So and it's rare. You'll see them sometimes, but I honestly right now I don't think I even have anything in the house that has the side spade to it like that. But they are out there. So again, when you look at your building prints or something like that, you have to base on what's required. If you notice, the top plug is a very typical 15 amp one. But if you do have stuff where you're going to expect to run 20 amp stuff, I don't know, for some odd reason, maybe they have a receptacle where they're going to have like a dedicated space heater or something goofy like that. You could end up where you have the one where it's a side spade. Now, quite often you'll run into one of the bottom two, and these would be like for like window air conditioners and that kind of thing. So that way you can differentiate. You know, you're not going to be plugging in your vacuum cleaner into a 240 line or something and blowing it out. So, and that's the main purpose of these things, you know, is make sure you have the right connection for what the device is. So, and these are these are the most common styles you'll run into in a residence. Of course, the top one here being the number one most common, but you will see these. And in some cases, they even have like different colors to highlight it, you know, oh, this is this. But yeah, the top one is the most common one you'll run into, but it should show you the common receptacle configurations and how they're used and what they're used for. Okay. And then we get into thing, and as you go along, eventually, so you get the toggle switches, right? Light switches and whatnot, you know, switch for your garbage disposal, whatever you. But the toggle switches, the Underwriters Laboratory. Now, Underwriters is the one that does this, okay? But it was picked up, and it's almost like a common way to refer to it. They refer to it as a snap switch. And that's because when you do, it's like a mechanical, that's that little click when you flip it up or flip it down, and that's a snap. But Underwriters is the one that refers to it as a snap switch, right? Typically, they're toggle switches. But the thing is, toggle switches can come in all kinds of shapes and sizes. So they want to differentiate. There's a couple of rules they go with. And even to the point where, like if you have a snap switch that is marked with the on and off symbols, there's a requirement for that where you cannot, by code, allowed to have it oriented wrong. That on is always faced up and off is always face down. If you install it like upside down, yeah, that's a code violation. One of those little things we'll run into for with using snap switches. Excuse me. But yeah, they can. They're pretty versatile. They can, if you actually look at, you know, every one of these comes with like a little spec sheet on it, if you will, which the most of us don't even read. It just gets thrown away with the little box it came in. But if you look at it, it does have actually voltage ratings on it, what it can be used for, and DC applications, what DC voltages it can be used for, that kind of thing. It'll even say what resistive loads it can handle. So some of them do have limitations. And the funniest thing is, you got to be careful of these, because if you did put in a toggle switch and the resistive load wasn't rated for, that could be something that you would be liable for. So you got to be careful with always check it. You know, if you get an odd configuration or an odd wiring, you know, make sure that, like even to the snap switch, make sure that snap switch is rated for the job it's going to do. So we always typically assume it's like, it's a snap switch, and it goes, but not all the time. Sometimes there's some oddball ones out there, but basically you would know. And like I said, anytime you get into an oddball one, just don't run into it. Kind of look at it and make sure that, okay, even this has to be looked at, make sure it's rated correctly. You know, it always comes back to what's your weakest link in the system, right? All right. And so we even look at general use snap switches. You know, they have AC only ones where they can handle DC. They can be used for resistive and inductive loads. Now, what's the difference? An inductive load is one where you're generally driving, and what they call it is like a coil motor, right? So, and that's an induct, it's magnetic in nature. So an inductive load would be anything that you're running a motor. Even believe it or not, your vacuum cleaner, right? It has an inductive load to it. Resistive load is anything else, like like hair dryers and that kind of thing, where it's being worked across some kind of filament or something like that. That would be a resistive load. Then it's driving across resistance. And it's something to remember is you cannot exceed, in a motor load, 80% of the current rating. And that's because motor loads tend to be heavy on the current. So if you were to exceed that over time, you would generally run that wire really hot. And over time, you could cause it to swell and eventually deteriorate and cause some damage. So just little things. It's an interesting little chapter. They even give you like some common configurations, right? So notice, right? So we have the neutral side. There's no brakes in that. So where's the switch? It's on the hot side to interrupt. And then the picture shows you a common lighting configuration, how you would wire it in. And generally, you'd do the wire pull. So you would have a break in there, right? You cut it and splice it. And remember, each one of these has to be no more than 6 inches long. And again, it's a good rule of thumb, basically, pretty much as long as your hand is to the tip of your thumb. And that's about an average of 6 inches. Measure it and see, and then you can eyeball and be like, okay, that's 6 inches. Because anything over 6 inches counts as two conductors when you're stuffing in a box. So if you get one of those little small gem boxes or something like that, one of the utility boxes, those things are tight and you don't want to overstuff them because, oh my God, what a nightmare. But um, but no, this is a pretty common configuration for wiring the switch up with a light, a lamp, lumen. Then we look at a couple other. I do like the pictorials that the book has because you could very straightway see it. Now, this is an oddball one, right? So you've got the red line there, if you notice, is like a carrier. So he never really carries a hot on him, right? So kind of a carrier or traveler, if you will. So he only will ever carry current when the switch is closed. When the switch is open, he never has anything on him, more or less. You got to look at the difference between like a traveler and a main hotline. I don't know, but yeah, that's a common configuration they have as well, where the source or the line load is up in the light box. And see now in this first picture, the source, see how it's coming up into the light switch box here, right? So that's where the hotline feeds into. So you just wire it up to the lamp as accordingly. Now, sometimes you will run into where the hot is up in the box, in which case then, yeah, you have to make like a traveler sort of line to it to this point. See how like the neutral is just capped off and not used there? That's because all the work is being done up in the box. The switch is just a break in the line load. Never break in the never break on the neutral. It's a waste of wire, but man, that's the drawbacks of using Romex or non-metallic sheet cable. See, it even says, right, type NMB, non-metallic. But what that sets us up to is a concept that we get into, and believe it or not, the three-way configuration can be a small nightmare for the beginner, okay? And it's how it's wired up. It can be a little tricky to wrap your head around. I'll be honest with you. I mean, everybody has a little trouble with it at the beginning just because of the way it operates. So this is like a schematic sort of diagram of a three-way, right? But when you really, oh, I don't want to get that. In reality, when you get a three-way switch, you're gonna have three screws on this thing, okay? Now, two on the side are both brass highlighted screws, and those work just like if you didn't use the third screw at all, It works just as a regular toggle or a snap switch. So if you just use those outer two, and it's overkill, right? Why would you do that with a three-way? Well, I don't know, who knows? But if you use those two outer brass screws on a three-way, it'll just be a regular snap switch. Now on the other side of the three-way, the screw is usually a different color than the brass, okay? And it's like a sort of almost like a blackish color. It's a real smoke. It almost looks like somebody had burnt the screw, if you will. Now, and that's what the sets up for the three-way. And a lot of people have trouble with this. If you ever have, when you go into a house, when I bought this house, it was like that. You know, people don't understand, you know, the regular person doesn't understand how a three-way works. So on my hallway light, I could flick the switch up, right? And it would turn the light on, but I couldn't go down to the other switch and turn it off. I always had to turn it off with that. Now, either switch would turn it on, but I didn't control both back and forth. And that's because they didn't use the traveler correctly. So on the on the three-way, they're pretty, it's a straight here. Let me jump up here real quick and kind of show you. So see, yeah, so you have two light switches and one lamp, right? A lamp is usually up in the ceiling or something like that. Um, but you have to match. You match your wires up to these crazy screws. So like I say, the two outer ones are typically the brass posts, the switches, if you will. And those are the ones that break the connection to the lamp itself. And the different colored one, if you see on this like diagram to the side, that's the traveler. See, both of these are snap switches and snap switches. And in this traveler, notice it doesn't have like really the line voltage on it, if you will. But what it'll do is that's the beauty of the three-way. So when you that way, when you do turn on the one light switch and you go down the end of the hallway and you can turn it off with that other light switch. And that's because it'll toggle back and forth between those two switches like that. That's always the trick of using a three-way, and people get that mixed up. And keeping that traveler together, see how from one switch to the other. So basically what you do is you take that you wire that smoky screw up from one to the other side and then control the light with the two brass colored ones, if you will, if that makes any sense. This is one of the labs I actually enjoy doing in class, because the three-way it's one of the more challenging ones just because it's so easy to miswire this thing. And then we threw and just because it's more fun, let's say I had a real lengthy hallway, or for some reason I wanted like more than two switches controlling a light, right? Well, you can't have more than two three-ways because of the traveler. So then they came up with a different concept, and that was the four-way switch. Now I can have multiple four-ways, okay? And so let's say, I don't know, if I had a mansion with an extremely long hallway where I wanted like a bunch, like I don't know, 6 to 10 different switches all down in the hallway, controlling the overhead lights, if you will. Well, two of those will be three-way switches, okay? Usually the ones at the beginning and the end. And then every switch in between that would be a four-way switch. And the four-way is just a crossover switch. He's actually a lot easier to wire up, and you will. It's the weirdest looking light switch because it has two screws on each side, and you just have to be careful. You know, identify, right? Identify. If your traveler's going in one configuration down there, well, keep that consistent through your switches. So you got to be careful flip flopping, and that's when like if you're using the Romex style, right, the sheath, you know, go ahead and use use your colored tapes, and that's where the other colors come in handy, like using a red or a blue or something like that to identify these things. And that way you can keep your wires consistent when you're running down these things. You know, it's like, okay, wait, no, the blue goes to this, the red goes to this, and keep flip flopping back and forth. But yeah, there's a typical a three switch combo, right, if you will. So you would almost think of it as having with a like a double traveler in a way, with the four-way switch in the middle. but just keep the consistency of the screws with that and walk your wires through and you'll be fine. If you wire it up and both of your three ways turn on and off the light like they're supposed to, but he only does it like half the time, then that means basically you would have to come back and flip flop one of these two sets because it would be crisscrossed. So it would be mismatched going back to the three-way snap here. And like I said, this is actually a little trickier than it seems, but that's just keep in mind, keep your wires identified, keep them colored, right? And then just walk them through, and then you'll always come out okay with that. If not, yeah, you'll get it where um, the light will turn it on, but the other one won't turn it off. That kind of thing. Yep, you've got a reversal of your wiring going on in there. That's a very, 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 very common home residence wiring where the guy knows just enough to wire stuff up but doesn't really know what he's doing. Yeah, a lot of homeowners really flub up on the three-way connection, if you will. Anyway, so then we get into one, and we talk about poles, okay? So in this case, we talk about a double pole. And what that means is you would have two switches, okay? And for whatever reason, they either have some kind of mechanical bond across them, right? Some breakers are wired up that way where you'll have to see like a metal tab going across both switches where they can't be operated independently. So that's what that dotted line indicates right there, okay? It's a double pole. That means two switches, but they're controlled together. They can't be operated independently. So that way, when both connect, like in this case, right, when you have a 240 double switch, like a double breaker going in there, you can't throw it independently. And yeah, like I said, this chapter is weird. It's got a bunch of stuff in there. What the heck is an inductive heating? Well, that's like I said, inductive. Generally, try to think of coils. Okay, coils in motors. Usually, motors are inductive loads, and when you're dealing with something called inductive heating, it could be a few reasons. You could have a short in the coil. You know, maybe not enough to stop it from working, but stop it from working properly. And so it's heating that could be caused by that short in the magnetic field around the conductor, um, because everything's AC, so you always have a magnetic field going through the wiring, right? Let's say, I don't know, something's going on with it for some reason, something else is interfering with that line or something like that. And that's why like they usually code requirement, you have to be at least 36 inches away when you have like media lines and stuff going with AC because they can interfere with each other. So you might have something going on with that, and it's causing the magnetic field of the AC line traveling down to start whacking out. You know, it's trying to do its job, right? But for whatever reason, now it's got an overdrive going through that. But yeah, typically it's like a short. It could be a short caused by something somewhere, but it's still operating, just not operating quite correctly. So what they say is you have to run these things together. Because if you had, like, if they're all on the same line and you have to travel them together, they're all running, you know, the same AC signal. If you had like one in a pipe and one not, this can cause trouble. So what'll happen is they're trying to balance each other out, but the pipe in the middle for some reason is interfering with it or grounding it a little bit, so it's causing a power loss. And then what happens is your current tries to drive up higher to overcome that power loss. Then you can get a certain amount of heat going on with that as well. So pretty much keep them all bunched together, keep them all together, everything going together. Yeah, because anytime you have a conductor carrying, when you have an AC signal, it's the very name, it's alternating, it's constantly shifting. And because of that, it's always driving. So when it does that, it kind of basically almost think of it like humming in a way. And in certain cases, if you get near like the large power lines, you can almost sort of hear that hum, right? Well, what you're hearing is literally the alternating signals happening in there, and that's what's making that hum. Some transformers might do it. Um, so the more current you drive, the bigger the magnetic field. So if you do have like some weird imbalance going on or some kind of weird short where the current's trying to drive even higher, it's making this, trying to overcome. And then with that, anytime you do, greater work, greater heat. Always remember that. And that's very much true for electricity. And in electricity's case, heat is not your friend. So you have to make sure that you run these together. Um, it's basically balance, right? So your hot and your neutral have to go together. They're running the same line, if you will. One's going in, one's coming out, right? So if they're run separately, so let's say I ran my hot inside of a EMT, and for some, who knows, for some bizarre reason, my neutral's on the outside. Well, that EMT in the middle almost act like an interference, right? So now one or the other is going to try to drive up higher to overcome that imbalance. It's the weirdest thing. But yeah, the rule of thumb is basically the hot and the neutral, yeah, they go together as even if you have to tape these things up over a given real long run or something like that, but yeah, always keep them together. One doesn't go on the outside of any kind of metal of any kind at any time, otherwise, yeah, you're just asking for trouble down the road. I hope that makes sense. It's kind of a weird concept, but yeah, like in this case, see how they're separately outside of the very bottom one? That would be two pipes basically. So one has the hot and one has the neutral. Yeah, that's literally going to cause like a weird a way to look at it is like a shorting problem, because now the AC is like, what the hell? And so that magnetic field from the line itself, right, is literally going to try to overcome this. So yeah, always keep everything together, always together, no matter what you have as far as what comes out on the end and whatnot. But for whatever reason, you had to attempt to try to run the neutral as a separate run like this, or you have the pipes going together to the same place and forget and got mismatched or something like that. Yeah, you're gonna have major problems with this one right here. So yeah, like I said, it's just a weird chapter. It's kind of fun. We're getting to the end here, so I hope I'm not boring the hell out of you guys. But oh, my bad. So combination wiring devices. What the hell is that? Um, there's a couple out there that you get them in some of the houses. Like here, let me show you. Yeah, where you get a switch and a receptacle built into one kind of thing for, I don't know, maybe you did an add-on in the bathroom later on, and really this is all you're bringing in is the one receptacle and the one light switch. You get them in different flavors. They even got these weird little dip switch style ones for lighting and whatnot, for space requirements and things like that, how to get multi-switches into a very narrow area. They got these blank up ones where they got these little modules. They literally snap into those right there, those little tabs. Yeah, that'll lock in, and you can mix and match and almost like create your own little light switch thing. And then yeah, they'll make weird cover plates for them too. But yeah, you run into combinations. For whatever reason, it's like space requirements. You can run it in tighter areas where you didn't have a lot of like wall room or something like that going on. Those are, a later addition, or they put lights over the vanity at the much later date, that kind of thing. And for space, you'll run something like this. Totally acceptable. It's a fun little chapter. It's just like do's and don'ts, going over things and stuff like that. Proper bonding. I like the pictures on these things, right? And this is the way I would always do this. And I remember when you do run into an outlet, right? Any kind of box that you're going to have a device in. As long as the run through terminates at that, like in this case, okay, so you just have those 3 wires coming into this box and they're just going to go to this one receptacle. You don't have to have pigtails, okay? So this is allowed to come straight in, bump, bump, bond right to the receptacle itself. And you have a ground post inside of the box most of the time, so you ground to that and ground to the post of the receptacle itself. So that protects, you know, if anything were to happen to the, you know, to the receptacle, that's the outside of it to keep it from bursting into flames, right? But this would be a very standard thing. Now, if you had more than one receptacle going into this box, like in this case, don't wire directly. Basically, what you would do is you're gonna start splicing, and literally to each receptacle that's gonna go in that box, you would make what they call pigtails. So you would have inside there, you know, you'd have your main feed coming in, and then if you had like 2 receptacles, you're gonna make 2 pigtails for hot, 2 pigtails for neutral, and 2 pigtails for ground, and connect them all together and pigtail them out. And again, remember, 6 inches, 6 inches. Anything over 6 inches, it's 2 wires. Even if it's only 1, it's 2. And that's how, you know, when you have to do size requirements for this stuff, 6 inches is a single wire in a box. Anything over 6 inches in a box is 2 wires. Even if it's just, it's just a technicality, but even if it's 7 inches, it still technically would be considered 2 wires at that point, if that makes any sense. But anyway, so yeah, we look at the bonding styles, right? And again, so you know, you want to be careful when you do ground, and it's going to be a bare wire. And this is a neat little see how on the wire connector, it actually has the pigtail built into it already. And you buy them these ways. It's actually kind of it's a time saver. You can so that way you bring your grounds in, you know, you got splices going on, right? So you can bond them all together here and still have that single pigtail coming out to go ahead and go on your receptacle. And there's different ways, you know, as long as you're bonded with ground, how you connect up. You can have the crimp on with the little spades, right, like that. Or even the little spades coming in from the ground connector going out and stuff. There's different combos, but as long as you got it bonded correctly, going to the device that you need to. And in this day and age, a lot of these, see, this is a metal box, right? But a lot of them now we're dealing with the plastic, so you wouldn't even have the bond screw inside there like that. So you'll probably be splicing and going directly to the receptacle, if you will. But yeah, there's a lot of different connections, and like I say, this very bottom one, that is one handy damn ass time saver to have, especially when you're going through roughing out, you know, where your plaster guys have all gotten done, and now you're ready to start putting in all your devices, receptacles and switches, and even some lights in some cases, right? You'll go through and I don't know, I always used to go through and start tossing out. You go through with a box of receptacles and put receptacles where they all need to be and whatnot, and go roughing out. Yeah, you go roughing out, and for a time saver, having those little pre-built pigtail green connectors, they're nice to have. But and that's pretty much my lecture for you guys today on chapter 5. It's a fun little chapter. There's not as far as the homework, you'll be happy to know there's not as many calculations to go through in this versus the other ones. But no, that's what we have. We'll have the homework for it, and then the next one we'll go into, I think will be, I gotta looking ahead. We do chapter 6, and then we'll start getting into, there's one where we do like a combo. I do like chapters 15 and 19 and something else all together, but that's so like next week and stuff. But so are you guys doing okay with everything? Is there anything we need to work on? Do we need to change anything? You know, I'm pretty open.
Have you got the tables yet for
the NEC? No, I said that at the beginning, right? I might not be able to get the electronic copy of the NEC. So that part of your calculation. Now I did post up a finished on today's tab. If you look, there's a finished service, or yes, or Monday's tab. I can't remember, but there's a finished one with all what I would consider the correct answers. If you want to go and compare that, there's no fail on this one. Okay, this is like a lab, and what I wanted you to do was be able to. I mean, as long as the highlights, that the worst grade you could possibly get on the service entrance things would be like a 70. Very, very worst grade ever, right? But I want to make sure you're in the ballpark, and if not, this is one of those ones where we can start working over. Like, okay, why did you pick this? And the biggest one is doing your branch circuits, figuring out your service speed, and then sizing the appliances correctly is very typically the hardest one. You know, and when in doubt, remember on this stuff, you know, if you think you're in on a lot of this stuff, if you're hedging a line, size up. Never hurts to be one size higher. Granted, as far as your materials list goes, you know, you start jumping up too much in wire sizes, yeah, you're going to be increasing your overall cost. But for things like, especially like appliance loads and the service entrance, we got to be careful on those because, again, so basically, and why? You got to think about, if I'm, all right, I got three things I'm dealing with when we do electricity, right? Ohm's law. We got voltage, we got current, we got resistance, right? So here's a good example for you. So if I want my voltage fixed. I got 120, 240, right? That's fixed. So if I got a wire going over a given length of time, space here, like really, let's say a really long run. Now the wire resistance, granted, is fairly low, right? But when we do a long run, that resistance factor increases, and what we get is something they call attenuation on that. Now, so if my resistance goes up, my voltage stays the same, what's going to change here then? Your current. And this is the factor that you have to watch out for. So, and think of it, right? So let's say I used a number 4, you know, a good size wire. And for most normal applications, this number 4 would be great, right? But let's say I'm a little too lengthy here. So, and what's going to happen is the current is going to try to drive anyway. It has no choice, right? So if the current tries to drive up and keeps pushing up and up to try to deliver that voltage, right? Because that voltage has to stay at that 120, 240. So if the resistance increased, the current has to go up with it to try to produce that voltage. And what's going to happen then? Well, the current starts going up, more current, and your wire is only rated for this much, right? What's going to end up happening? Well, we overexcite the damn copper. And when you overexcite the copper, this stuff gets damn hot. And that's what we're really trying. I mean, that's really it in a nutshell, what we have to deal with, right? So we don't want the wiring, because if the wiring gets exercised too much, right, the heat ratio gets, granted, in the beginning, it'll probably be able to handle it and whatnot. But over time, no, things are going to start to degrade. Your insulation is going to start to degrade because it's rated for only so much. And if I'm producing heat factor way, way up over what its normal threshold is, your insulation is going to start giving out, right? Or I get to, I don't know, no wiring is perfect. What if then some of those strands or something like that, I got a couple of weak points. Well, those start giving out. So if I start giving out in my multi-strands, you know, over a given run, that's just going to, in fact, increase the problem, isn't it? So eventually I'm going to start getting mini arc flashes going off, which again are producing more heat. And eventually this damn thing is going to melt through somewhere and we're going to have some major issues. But, and that's what it is, right? And I mean, really, because it's only dealing with Ohm's law. You have those three factors that you always have to deal with. And remember, your voltage is your work. So the voltage at the end is my work potential, right? So if I say I got 120, 240, this is the amount of work I am going to produce. But if I have other factors in there and current has to try to compensate for the amount of work I'm doing, yeah, we're going to have trouble. So always remember that, if it starts to get to that threshold and how much of a percentage you're allowed to drop, which isn't very much, right? So always size up, size up. It may seem like it's a little overkill, but really looking at it, you got to really think your biggest flaw in that whole thing is the wire size and the distance. Otherwise, that formula is fairly consistent, and that is an Ohm's law formula, by the way, where it's literally taking the voltage, the current, and the resistance, and the way we juggle it around, I know, right? So we got the K factor for like copper or aluminum conductors, right? And your big thing in there is the distance. So if you got your certain diameter of this stuff, and that's where circular mills come in plays, right? Um, and the distance factor. So the distance factor changes that. Yeah, that's gonna our biggest change is gonna be current. Just so I mean, just keep aware of that when you're doing this. And I know it seems like a very weird formula, but that's a very typical. And now and if you look in your uglies book on that one, that's that formula you look under, it's a single phase formula. Now don't get them confused, because residences are single phase, 120, 240, okay? But they also do, because it has industrial applications, there's one in there for three phase. And that's if you're dealing with a 277 480 combo. And that's an entirely different animal. And that's actually even a bit more of a calculation, if you will, because of the three phase. Very similar formulas, just a little variation to it. But yeah, always remember we're dealing with single phase systems when we do resonance, and that's the formulas you want to stay with, are single phase. Because I know the Uglies book spells it out. And then otherwise, I mean, really, then we're just looking at conductor sizing. You got to look at the zone you're in, right? So we would normally be working in our temperature zone, and then what your insulation, and where's your weakest link in this thing is wire sizing, and your insulation factor can kill you. So the type of insulation we're using, what's the temperature rating of it, right? That's why I always spell out. It's like, well, we were in Arizona, because compared to here, Arizona would be a much different animal, and you would definitely be running some different insulation types than you would here. but yeah, with that, yeah, answer those as best you can, Jared. Going through there, I do have the one posted with the thing. I don't know when I'm going to be able to, or if I'm going to be able to get a copy of the NEC posted for us to use. I don't know if there's like supposed to be a classroom license for it or anything like that. And it's all these, I'm going through so many channels with that right now. It's kind of goofy.
Okay.
Otherwise, the rest of the stuff I know from this point is a lot of Uglies book calculations and the tables and charts that are in the textbook.
Yeah.
This one was the only one where I was really, highlighting more of a use of the NEC, just looking up the tables and charts in there so you were aware of them. Like I said, it was more of a lab exercise, and I wanted you guys really just to get familiar what all goes into, right from the beginning, right? Like I say, every company you work for will have, if it's a good company, will have some form of that kind of sheet. They'll have their own letterhead on it, it might be laid out a little differently, but usually they have that kind of something, a lot like that kind of sheet to go through when they do like a job bid or something like that. But that's all that is just like an introduction. So you realize, holy cow, there's a lot of crap that goes into this. Hopefully it didn't frustrate you too much, but everything else going good. We're able to get everything in. like I say, if you have trouble with anything, really, you gotta let me know. I'm definitely here. I've opened, compared to doing this at school and stuff, I've opened up where I'm answerable most times of the day and things like that. I try to be. I mean, I'm not there, Johnny on the spot 24/7, but I ain't gonna promise that. But no, anything you guys, I'm seriously, if you're having trouble with anything, let me know, and then I'm sure there's a way we can work it out. Even to the point where if your computer's crap and it ain't working right or something like that, let me know. I know the school was even giving out Chromebooks and stuff like that for you know like a checkout from the TLC, the library. But anything like that, yeah, definitely let me know, and then we'll work through it. This is not meant to be like frustrating, right? We're supposed to be having fun and learning from this. Because this class is kind of set apart. I mean, a lot of the stuff you'll be able to, well, a lot of the stuff you can use over in, if you decide to pursue like an industrial electrician style thing, a lot of this stuff is transferable, but it is meant to be more exclusive to the residential side. And that's why I spell out that single phase versus the three phase. When you get into 150, if you go to 150, that's where you start dealing with three phase and whatnot. But for this class, yeah, we're very single phase oriented, and most commercial applications will be single phase. And granted, there are variations to that as well. I mean, you got to take everything with a grain of salt and do it as it applies. Will you get out of here, Doug? But yeah, every residence very typically, the line you have coming in from the outside will be a single phase setup. Oh, Doug, get out. But so no, you guys have no questions or anything? We're all good with everything so far?
Yep.
All right. Well, gentlemen, I have the new homeworks posted up for you to go through. Like I say, if you have any questions on any of that stuff, let me know. Tried to keep, it's not like in the back of, each chapter, there's an extensive amount of questions. I didn't go through all of them. I wanted to keep it where it's more doable and not frustrating stuff for you guys. But yeah, let me know if you have any trouble with anything, and we'll get it worked around some which way. We have no questions, nothing.
No.
All right. Yeah, I hate this because usually in class I get to see your faces and wake you up if you're sleeping.
Well, trust me, you don't want to see my face today.
Stay at home, or you got your day pajamas on versus your night pajamas. I was watching, who the hell was it? I think James Corbin was saying it. He goes, yeah, I had to break up my day from my day pajamas to my night pajamas. And I was like, that's actually funny. But, all right, gentlemen. Well, you have a fantastic weekend. Hopefully it doesn't rain and stuff too much, but at least it'll be warmer finally.
Hopefully.
Yeah, I know. It's been a weird year so far. But all right, guys, I'll see you on next
Thursday.
Yeah, definitely. And let me know if you have any problems with anything, or otherwise, have fun with the homeworks and all that. All right.
As much fun as you can have with homework.
Well, I know. I try to make it fun. At least it's it's kind of interesting. It's some of the stuff is, some of it's just like I know the formulas can be a little frustrating, and that's why I was just trying to emphasize and drive that home. It's like, really, that's all the factors we ever really, and that is all the factors we ever deal with, right? We've got voltage, we got current, we got resistance, and that's our very typicals. And then the only other thing we'll plug in there, and I mean, it's right on the front of your Uglies book, right? And then we got the power rule. So between the two, it's like, all right, I figure out how much power, I figure out this, and then that's it. And everything from that is always combinations of that, depending on what you're looking for. You know what I mean? And usually you don't have to do a whole lot of calculation through it, but yeah, that line drop one is pretty important, and basically figuring out what motor requirements, that kind of thing. The specialties that go a little over and above, kind of thing. Um, but otherwise, everything else is pretty straightforward, and for most things, you're doing like a repeat, the same thing. And just like I say, you always got to watch out for your appliances, furnaces, air conditioners, and dishwashers and garbage compactors, or maybe the guy wanted to have 6 washing machines and 6 dryers in his house or something crazy. But you always get every now and then you'll run into some weird ones where you're like, huh, I guess I never thought about that. But it can always be done. It's just a matter of figuring it out. No. But all right, I'll see you guys.